Hi all. I'm very excited to get an opportunity to speak with you about what I think is one of the more interesting topics in all of math, certainly in Calc 2, and that's integration by partial fractions. Now, because we are doing this through a distance format, I'm not going to get into the more rigorous, difficult problems, but I think you'll see that even these that I'm going to talk about in the video are pretty fun to work with, and it will give you the concepts that you need down to understand the problems. So as some background, what I'm starting off here, I'm having you recall what we did in algebra classes. One of the main things that we do in algebra classes is we remember anytime you're supposed to add or subtract fractions that have a different denominator, you say, well, you can't do that unless you get a common denominator. So if I were to give you a problem like this, you would go into the first fraction and say, well, I need to multiply it by x plus 1 over x plus 1. And the second fraction, you'd need to multiply it by x minus 3 over x minus 3. And then the resulting fraction would have that common denominator of x minus 3 and x plus 1. In your numerator, you would have 2 times the x plus 1 minus 1 times x plus 3 in order to obtain that common denominator. After that, you would just go through and say, well, you'd have 2x minus x for 1x when you simplify your numerator, and you'd have 2 times 1 is 2, and then a negative 1 times a negative 3, that's going to be plus 3, so I'd have 2 plus 3 is the 5. And we would have our final fraction, x plus 5 over x minus 3, x plus 1. So we did that in algebra class quite a lot. Now, what we're going to have to do in our class, and you need to remember why we're doing this. Well, whenever we integrate, you'd prefer not to have that complicated fraction because we don't know what to do with it necessarily. But if you had the integral of these two simpler fractions, you can say, well, every single time if the derivative of the denominator is in the numerator, then it's the natural log of the absolute value of that denominator. So I could look at this one and just say, well, if that were inside of an integral, that would be 2 natural log of the absolute value of x minus 3. And then minus the derivative of the denominator is in the numerator, so this would be minus the natural log of x plus 1 if these two were in individual logarithms. But if I had the whole fraction, I wouldn't necessarily know what to do. So these individual partial fractions are superior than the whole together fraction. So we need to do these problems in reverse for what we're doing in our class. So partial fractions, case 1. All I'm doing is I'm looking back at this problem in case 1 and showing you how it would work out. So let's say we started with that integral of x plus 5 over x minus 3, x plus 1, and we're integrating that with respect to x. The first thing I would have to do is decompose the fraction into its component partial fractions. The way we do that, and case 1 is always when your denominator only has linear factors. Well, this denominator certainly has linear factors. The linear factor x minus 3 and the linear factor x plus 1. So every single time that that's the case, what you're going to do is you're going to break this apart and say some constant a over the first linear factor plus some constant b over the second linear factor. However many linear factors you would have, you'd keep on adding c, d, e for however many you had. In this case, I just had 2, so I only needed a and b. But now I need to find out what the number a and what the number b are equal to. So what I've done from this step to this step, notice the left-hand side, it was the entire fraction. Now it's just the numerator. Well, all I've done is I've multiplied the entire equation that I've designed by the least common denominator of x minus 3x plus 1. That gets rid of it on the left-hand side. On the right-hand side, if you multiply by x minus 3 and x plus 1, the a is only going to be multiplied by x plus 1 because the x minus 3 canceled. Whereas the b is going to be multiplied by x minus 3 because the x plus 1 would have canceled with the x plus 1 you were multiplying by. So now my goal is to solve for a and b. The easiest way to do that, guys, is to let x equal values that cause your factors in the denominator to be 0. So notice here I said, well, what if x equals 3? Then you'd say, well, then that factor in the denominator would be 0. I let x equal 3 in my problem. On the left-hand side of my equation, 3 plus 5 is going to give me an 8. On the right hand, I'll get a times x plus 1, that's a times 3 plus 1, plus I knew that the b term would cancel out because b is multiplied by x minus 3. Well, 3 minus 3 is 0. So notice, as long as you plug in the values that cause zeros in the denominator, you're always going to have one of your constants cancel out. In this case, the b canceled out. So I'll have 4a is equal to 8, and thus I can say a is equal to 2. Now, when I try to solve for b, and you can look up here and say, well, what do you need to let x equal in order to solve for b? I would need to let x equal -1, and I guarantee you, if I can let x equal -1, I'll get a solution for b in the problem. I go down here to my equation. X plus 5 becomes -1 plus 5. On my right-hand side, I would get a times -1 plus 1, that's a times 0, plus b times -1 minus 3, that's going to be -4b is equal to a +4. And I know if that's the case, I could divide through by -4 on each side, and I'll get b is equal to -1. Now I have my solution for a, and I have my solution for b. So the whole point of these problems is that we rewrite the original problem as two simpler integrals. So I can say this integral is equal to the first partial fraction, which was a over x minus 3. So I'll say the integral of 2 over x minus 3 with respect to x. And then plus the second partial fraction, b, which is -1 over x plus 1 with respect to x. And then, just like I mentioned up at the top of the sheet, once you get those inside the integral, it's easy because you say every single time if the derivative of the denominator is in the numerator, it is the natural log of the denominator. In this first case, all I had to do is factor a 2 to the outside, natural log of x minus 3. I brought the -1 out in front of the second one, and I would get natural log of x plus 1 plus our constant of integration. If we needed to condense that down, which sometimes we'll need to, I think Achieve likes you to have a condensed answer, you'd say, well, this is going to be the natural log of the group x minus 3 quantity squared divided by x plus 1. Remember, anytime you subtract a log, the terms inside that log go in the denominator. So divided by x plus 1 plus the constant of integration. So now I know what you're thinking. You're thinking, well, that's a pretty cool problem. This is the easiest case. Let me do another case 1 type problem. This one's still the nice, easy case, but as I said in parentheses here, this one's more fun. What makes this one a bit more fun than the previous one? Well, in this one, you're at least going to have to factor your denominator first, and that's a key. You absolutely must factor the denominator. The numerator should not be factored. It's better out in polynomial form. But that denominator must be factored. So you'll notice the first step I did in this one, factor the denominator. I first factored out an x, and you'd be left with the trinomial x squared minus x minus 2. And then I said, well, I can further factor that. Factors of -2 that sum to get to -1 are -2 and 1. So I know that this denominator factored to x, x minus 2, and x plus 1. Now it was a matter of I needed to rewrite this overall fraction as a sum of partial fractions. So I knew for each linear factor in the denominator, I needed a constant numerator. So I have my numerators a, b, and c over the factors of x, x minus 2, and x plus 1. Now to go from this step to the next, all I've done is I've taken that entire equation and I've multiplied by all of those denominators. Notice that's why my left-hand side is still the numerator, the 3x squared plus 7x minus 2, now with no denominator. So I multiply by these terms on the right, and that's going to give you a times the other two factors, x minus 2 and x plus 1. B times the other factors other than x minus 2, so B gets multiplied by x and x plus 1, and C will get multiplied by x and x minus 2 here. So now I have my equation set up to where I can try to solve for A, B, and C. And each time, guys, you can easily look at it and say, well, how do I solve for A in this problem? You let x equal 0. So if I let x equal 0, look what happens in my problem. The left-hand side, you're just going to get a negative 2 when you plug in a 0. On the right, the terms of b and c cancel out because they both have a factor of x. So that's b times 0, c times 0. But the a is going to be multiplied by 0 minus 2 and 0 plus 1. So a is just going to be multiplied by negative 2 times 1. That's giving me negative 2a is equal to the negative 2, which means a is just 1. So that's the first step that I need to find out my partial fractions, the term of a. I go on and I say, well, what do I need to do to solve for b? I would let x equal 2. So I come down here and I let x equal 2. Please notice I'm just plugging 2 into that polynomial on the left-hand side. That's nothing more than f of 2 there. Now on the right-hand side, I knew that the a term and the c term had to cancel, and that needs to make sense to you guys. It cancels because if I plug in an x equals 2, a is multiplied by 0, and c is going to be multiplied by 0 because they both had the factor x minus 2. When I plug a 2 in with a b, it's going to be b times 2 times 3. So I get 6b is equal to, and on the other side, it's simplified out to be 24 because you would have had 3 times 4 is 12 plus 14 is 26. 26 minus 2, 24. So I have 6b is 24. I divide by 6. I'll get b is equal to 4. Now I have solved for a. I've solved for b. Let's see if we can get c. And you know you can, because all you need to do is let x equal negative 1. And you say, okay, if x is negative 1, again, you plug it into the polynomial on the left-hand side. And there is no point in even thinking about what a and b are multiplied by because it's guaranteed to cancel. A would get multiplied by a factor of 0. B would get multiplied by a factor of 0 whenever you're plugging in x equals negative 1 into those. So the only one you need to worry about is the one with c, and c is going to be multiplied by negative 1 times negative 1 minus 2, which is where the negative 3 comes from. Well, I know negative 3 times negative 1, that's going to be 3c. My left-hand side ended up giving me 3 minus 7 minus 2 for a minus 6. So 3c is negative 6. I know c is equal to negative 2. Now I have my solution for a, b, and c. My notation here, I is always equal to your original integral in the problem. So I said the original integral of the problem, which is up here, is equal to these 3 separate partial fraction integrals. So the first one, a over x, well, that's the integral of 1 over x. Plus the second one, b over x minus 2, well, that's plus the integral of 4 over x minus 2. And then the third one, I have plus c, or plus negative 2 over x plus 1. Once you're at this point, it's extremely easy, guys. We say every single solitary time if the derivative of the denominator is in the numerator, the answer is the natural log of the denominator. So we get natural log of x plus 4 natural log of x minus 2 minus 2 natural log of x plus 1. Of course, that 4 and the 2 we could have brought out front and then said the 1 is the derivative of the denominator. The only thing I've done after that is I've made that answer even nicer by condensing that logarithm. You can say we have the natural log of x times x minus 2 to the 4th power in the numerator, and then this x plus 1 goes in the denominator, and it's going to be to the 2nd power since it was subtracted to the 2nd with a 2 coefficient. I add my constant of integration to wrap it up. Gorgeous problem. Now you're thinking, well, that's case 1. We need to see these other cases through here. Of course we do. Case 2 is just where you're going to have still only linear factors in the denominator, but those linear factors could be raised to powers. Now, this one typically confuses people because they'll look at it and say that's not a linear factor. They'll say, oh, that's a quadratic factor. Quadratic factors are only factors that are of degree 2 that cannot be further factored. So let me explain that in this problem right here. If I have this as my original problem, I have the polynomial 5x squared minus 3x plus 2 over x cubed minus 2x squared. The first thing I would do is factor that denominator. And I would say, well, it factors to be x squared times x minus 2. Now, whenever you're thinking of this, that factor of x minus 2 clearly is a linear factor. But I need you to think of x squared as a linear factor as well. And the reason why is x squared could be factored down into x times x. So when we think of it in this terms, it's nothing more than a linear factor that is occurring 2 times. So now whenever I go in and try to solve for that, I'll set up my integral, my numerator over the x squared times x minus 2. Anytime you have a linear factor that's raised to a power, as we have the linear factor x raised to the second power here, then for every single power of that linear factor, you're going to have a separate fraction. So please notice, a over x plus b over x squared, that's all for that factor. If that would have had an x cubed there, I would have had to put plus c over x cubed. If it would have been an x to the fourth, plus d over x to the fourth. Since I just had an x squared, I only have the 2 separate partial fractions for that. And then the linear denominator of x minus 2, I'm going to have c over x minus 2. Now, you can go ahead and look at the degree of the denominator here, and it's going to tell you how many letters you're going to have. So it was degree 3. You knew that you had to have an a b, and a c. Notice in my last problem, it was degree 3. You had to have an a b, and a c. In my first problem, the denominator was just degree 2, which is why I just had an a and a b. So that's a dead giveaway as to whether you're doing it correctly as far as breaking it up into the sufficient number of partial fractions. So now in this case, I had to break the x squared up into 2, the a over x squared and plus, the a over x plus b over x squared. Then I had my c over x minus 2. At that point, what I did is I said, well, let's multiply by that least common denominator of x squared times x minus 2 on both sides. When I do that, the left-hand side is just the numerator. The right-hand side, you're going to have a, and whenever you're multiplying by x squared, one of those powers of x cancels, and I just get x to the first, and you'll also have the factor of x minus 2. And the second one, when you're multiplying by the x squared, it cancels out that x squared, but you'll still have b times x minus 2. And of course, the c here, it was being divided by x minus 2, so it cancels out the multiplication of x minus 2, but you'll still have c times x squared. Now, when I pull it down into my problem, I can say, okay, in order to solve this out, I know I should be able to solve for a or possibly b, since both of these could be a 0 if I let x equal 0. So notice, I let x equal 0. What happens? Well, what happens in this case, if I let x equal 0, the a and the c terms cancel. So I'm not solving for a or c in this problem, but I am solving for b. If I let x equal 0, the left-hand side of my equation is just the constant, the 2. The right-hand side is going to be b times 0 minus 2, or negative 2b. I know negative 2b is equal to 2. I divide by negative 2 on each side. b is negative 1. Now, I go into my equation and I can say, well, in order to solve for c, you should be able to let x equal positive 2. I do that. When I let x equal positive 2 on the left-hand side, you just plug 2 into this polynomial, 5 times 2 squared minus 3 times 2 plus 2. We know that that's going to be 5 times 4 is 20, minus 6 is 14, plus 2 is 16. That's where this came from. On the right-hand side, there's no reason to even worry about the a and the b terms because they're both going to be multiplied by a factor of 0 when you plug in x equals 2. The only one that you're going to get is c times 2 squared. That's where I got the 4c from. So 4c is 16. I divide by 4, and I get c is equal to 4. Now, I come down and I can say, well, okay, I have my solution for b and I have my solution for c. Unfortunately, there's not any other number that you can plug in to solve, but you can use some logic here. And here's the logic that I used in this problem. Notice I put x squared over here. If you look at x squared, On the right-hand side of the equation, I need you to see b could never equal the coefficient of an x squared term. b is only multiplying x, and b is multiplying -2. The only way you're going to get x squared terms on the right-hand side are ax squared, because you'd have ax times x, you'd have an ax squared, and a cx squared. Well, I already know the coefficient of x squared is supposed to be 5. So I used that fact in order to solve for a. I said, look at your coefficients of x squared. On the left-hand side, it's a 5. What is it on the right-hand side? It's going to be whatever a plus c is equal to. Fortunately, we already know c is equal to 4, so that allows me to say a plus 4 is equal to 5, solve for a, and get that it's equal to 1. Now, whenever I'm looking at the rest of this problem, I would go in here and say, okay, that means that my original integral here, all I'm doing is I'm breaking up the original problem. This is a over x plus b over x squared plus c over x minus 2. Those came from the a, the b, and the c that we just did right there, so I'm not pulling anything from one page to the next. But then when you do that, a common mistake students do here is they get so eager on these problems. So many of the problems have natural log answers, so that they just want to say, oh, it's natural log of all those denominators. It's not in this case. The first and last one are natural logs. Whenever the degree of the numerator and denominator differ by 1, it is going to be a natural log. That's not the case here. So you say, well, okay, the first one is going to integrate to be the natural log of x. The last one, that 4 could come out, and you would have plus 4 natural log of x minus 2. That second one, however, what I've went ahead and done here is I said, well, that -1 could come to the outside, and then I would have x squared in the denominator. That's just x to the -2. Now, when you think about how to do that, you'd say, well, x to the -2, that's just going to integrate to become, we know that whenever you integrate, you add 1 to the exponent. So you'd say, well, that's going to be x to the -1 over -1. And then you could say, well, okay, but then you're subtracting that. That's why it became positive. And then x to the -1 becomes x to the +1 power in the denominator. So I can say all of that just equated to the plus 1 over x for that second term. And I went ahead and combined my first and third term. I had two positive log functions, so I multiply the terms within. The natural log of x times the group x minus 2 to the 4th power. That coefficient comes up as a power on that group x minus 2. And then I have the plus 1 over x plus the constant of integration. So you're thinking that one wasn't too bad. Let's look at one more case 2 type of problem. And again, the case 2 type of problem is always when we have some linear factor in the denominator that's being raised to a power. Your book will call it a repeated linear factor. It just means it's a linear factor raised to a power. In this problem 4, the power on the linear factor is, again, the second power. I have x plus 1 squared. So the first thing I do in this problem is I know it is not going to help me to try to leave the problem in its current format. I don't know how to integrate that. So I try to break apart this fraction into partial fractions. I'll say, since the denominators are all linear, my numerators are all constants. I have a over the factor x plus b over the first power of x plus 1 plus c over the second power of x plus 1. And again, if I would have had an x plus 1 cubed down there, no big deal. You'd have just had a plus d over x plus 1 cubed. And it's worked extremely similarly. But now for this problem, I can go in and say, all right, how did I go from here to here? I multiplied by that least common denominator of x times x plus 1 squared on both sides. When I did on the left, it just gives me the 3. When I do that on the right-hand side, I know that the x cancels with this x, and I would have a times the group x plus 1 squared plus b times x plus 1 to the first power. One of those powers of x plus 1 canceled. And the c, I know the x plus 1 quantity squared will entirely cancel out, but I'll still have c times x here. So now, in order to try to solve for the variables in the problem, I set each of my factors equal to 0. So I'm going to set x equal to 0 and x equal to -1. And I know good things will happen when I do that. Setting x equal to 0 doesn't affect the left-hand side. It's just a constant 3. But on the right-hand side, setting x equal to 0 cancels out the b and the c term because they'd both be multiplied by 0. The variable a is going to be multiplied by 1 squared, so I know 1a is equal to 3, which tells me, well, a is equal to 3. Now that I have my solution for a, I can go on and say, well, let's set x equal to -1. When I do that, again, left-hand side isn't affected. On the right-hand side, I know that any any constant that's being multiplied by a factor of x plus 1 is going to be equal to 0. This is a 0, this is a 0, so the only where I can plug in a -1 and it be worth anything is with the c. I'd get -1 times c is equal to 3. So solving for c, you just divide by -1 on both sides, and we can see that c is equal to -3. I have my solution for a, I have my solution for c. Yet again, I had to use another trick to try to think of how to solve for the remaining variable, in this case b. And here's how I did that. I said, let's look at the coefficients of x squared. Well, if you look on the left-hand side, there is no x squared term, which automatically means the coefficient of x squared on the left is 0. And then it's important to understand c can never equal the coefficient of an x squared. C is only multiplying x. But over here, b would equal a coefficient of x squared, as would a. So you can say, well, your coefficients of x squared on the right would just be a plus b. So I know a plus b has to equal 0, which tells me b is just the negative of a, which then I can say, well, b is -3 then. So I get a is equal to 3, b and c are both -3. Now I go down to my partial fraction. So I take the original integral. Anytime I put I, it's just the original integral. That original integral is broken into its 3 component partial fractions. The first one, a over x, 3 over x, plus the second one, b, which is your -3 over x plus 1, plus the third one, again, -3, now over x plus 1 quantity squared. The first two are easy. You just say anytime the degree of the numerator and denominator differs by 1, it's going to be a natural log. Derivative of x is 1. You can pull the 3 out front and call that 3 natural log the absolute value of x. Minus 3 pulled out front, then you'd have the natural log the absolute value of x plus 1. Please don't think that the next one is a natural log. The degree of the numerator and denominator do not differ by 1. It can't be a natural log. So this one, I'm just wanting you to remember the reverse chain rule works really, really well. If you think of this as -3 times x plus 1 to the -2 power, then whenever you integrate that, you can say, well, that -2 power, you add 1 to the exponent, becomes -1. You divide by that new exponent, and technically you would also divide by the derivative of the inside, but that doesn't amount to anything. So I can say, okay, now this -3 over -1, that's just going to be plus 3, and then I'll have x plus 1 to the -1. That means x plus 1 that goes in the denominator to the first power. That's where that term comes from. All I did after that was, again, I cleaned up my answer by condensing my logarithmic terms. I have the natural log of x cubed divided by x plus 1 cubed. That's where all that comes from. And then I have plus 3 over x plus 1 plus your constant of integration. Now, we've worked through 2 cases. The next case, and this is where students really usually start to struggle on these. Case 3 is when the denominator contains an irreducible quadratic. So an irreducible quadratic is something that cannot factor. And remember, sum of squares is not factorable in the real number system. So your x squared plus 9, x squared plus 4, things like that. It could also be a trinomial like x squared plus 4x plus 7. So it doesn't have to just be a 2-term. It could easily be a 3-term that's just not further factorable. So any irreducible quadratic. Now notice my original problem here, I had x plus 1 over x times x squared plus 4. The difference here in case 3 versus the prior two cases is how you must break it apart. So same thing for that first factor. You said, well, you have a linear factor of x, so I put a over x. Now what I'm wanting you to remember here, since that's a linear factor, its numerator needs to always be 1 degree less, so in other words, a constant. Well, if it's an irreducible quadratic factor, then that's degree 2. I need that numerator to be 1 degree less. So you say, oh, then your numerator needs to be a linear. Yes. I've already used a over here, so notice my numerator here is going to be bx plus c. The degree of the numerator, whenever you break apart these partial fractions, always has to be 1 degree less than the term inside of your fraction. In this case, it's an irreducible quadratic. Numerator had to be linear. Now, I'm going to have to solve for a, b, and c in this problem. So I'll go back over here, and also notice this still follows the same format. If you looked at the degree of your denominator, you'd have said it's degree 3. So before you go into this problem, you should have known that you would have an a b, and a c to solve for, and we do. Now I come down here and I can say, well, in this problem I would multiply by the least common denominator of x and x squared plus 4. That just gives me an x plus 1 on the left. On the right, I'll have a times x squared plus 4 plus the group bx plus c times x. Now when I'm trying to figure out what to do with that, I can let x equal 0. Now notice this this irreducible quadratic, you can't force it to be 0, so that's not helpful, but that first one is. I can still let x equal 0. When I do, the left-hand side of my equation is just a 1. The right-hand side of my equation, I can see that the b and the c terms would be multiplied by 0, so they cancel out. A is just going to be multiplied by 4. I get 4a is equal to 1. A is 1/4. Then I can say, okay, I don't have any other numbers that's helpful to plug in because there's nothing else I can make either of those factors equal to 0. But instead of worrying about that, all I need to do is look at the variables in the problem. And notice, you don't have a term of x squared on the left-hand side, which means its coefficient would be 0. Look at what the coefficients of x squared could be on the right-hand side. You'd have an ax squared, and you would have a bx squared. C cannot equal the coefficient of an x squared. So you just say, well, on the right you'd have a plus b, and you know a plus b must equal 0. So again, that tells me b is just the negative of a, and b has to be negative 1/4. Now, when I'm looking at the c term, all I did for that is I just said, well, notice c has to be the coefficient of x, and that's it. A cannot equal a coefficient of x. A is going to be the coefficient of x squared, and then you'd have the constant 4a. B is only going to be the coefficient of an x squared term. C is the only coefficient of x on that right-hand side. The only coefficient of x on the left is 1. So by process of elimination, that tells you C has to equal 1. So I take that value of A, B, and C, and remember, on my next page now, I'm going to have the integral of a over x, so that's going to be the integral of 1/4 over x dx, and then I'll have plus bx plus c over this term. That's going to be negative 1/4 x plus 1. That's what I tried to do right here. So that's my a over x plus bx plus c over the irreducible quadratic of x squared plus 4. Now let's talk about how to attack this. Again, the first one's easy. Anytime the degree of the numerator and denominator differ by 1, you might as well just say it's going to be the natural log of that denominator, and I can bring that 1/4 out in front and say, well, it's 1/4 natural log of x. Now, the second one. Yes, again, I see, well, the degree of the numerator and denominator is going to differ by 1, so I know a logarithm is involved somewhere, but in order to force a log in this problem, I would need to see the derivative of that denominator in the numerator. Well, the derivative of the denominator would be 2x. There's no way to get a factor of 2x in that numerator. So that's not going to work altogether. That's why I broke the numerator into two separate integrals. So notice what I've done here. As I said, let's think of it as I have 1/4 over that denominator of x squared plus 4. What am I going to do? I'm going to factor out that minus 1/4 in front and call it x over x squared plus 4. But then you can say, but you also have a plus the integral of 1 over x squared plus 4. Absolutely. So you can always distribute the denominator into each term in the numerator and separate your fractions that way. So now I can say, okay, these should be easier to work with. In this first one, I can say as long as I can see the derivative of the denominator in that numerator, then it's the natural log of the denominator. Now looking at this, you can see, well, it's not quite there. You would need to have a 2 up there. If I need to multiply by a 2 on the inside, I'd need to divide by 2 on the outside. That's why you see a minus 1/8, the natural log of that denominator for the second term. The third term over here, we've worked problems out like this in earlier sections, and you could easily do this by substitution if you wanted to. That's not really the point of these problems, so I'm going ahead and taking the chicken route out and saying, hey, there's a table formula for that. It's one of our inverse tangent formulas. 1 over x squared plus a squared, or 1 over u squared plus a squared, is 1 over a inverse tangent u over a plus c. So I can see, well, the a in this problem is just 2 because a squared is 4. So you could say this has to be 1 over 2 inverse tangent of x over 2 plus c. That's where that comes from. And then you can say once you get to that point, all you needed to do is combine your two logarithms. This is going to be the natural log of x to the 1/4, or the 4th root of x. And then in my denominator, I'll have the 8th root of the group x squared plus 4, all inside the natural log, plus my 1/2 inverse tangent of x over 2, plus that gorgeous constant of integration. Now, case 3 was when we had an irreducible quadratic. Case 4 is when we have that irreducible quadratic raised to a power. So notice my example for this one. I have the integral of 2 with respect to x over x times the irreducible quadratic, x squared plus 1, quantity squared. So I can say, well, all right, I know that whenever I had the powers on linear terms, you had to have a separate fraction for every power of that. It's the same case here, guys. So now, though, that factor is no longer linear, so every numerator has to be, every denominator is going to be quadratic, thus every numerator has to be linear. My first term is just an x. I can handle that with the a over x again. Plus, every power of this needs a separate fraction, so you'd have x squared plus 1 to the first power, and your numerator is going to be bx plus c. And then plus the next power of x squared plus 1 is the second power. You need a dx plus e. Again, though, remember, you should always know exactly how many letters you're going to need in your problem if you just look at what the degree of the denominator is. The degree of this denominator, x squared squared, is x to the 4th, times x is x to the 5th. It's degree 5. You knew that you would need an a b, a c, a d, and an e in this problem. We have all of those. So now that helps assure you that you've set up your partial fractions correctly. We need to solve for those a, b, c, d, and e. So I come down here and I can say, okay, I multiply by the least common denominator on both sides. Left-hand side is just a 2. The a is going to be multiplied by x squared plus 1 quantity squared. The bx plus c is going to be multiplied by the 1 factor of x and 1 factor of x squared plus 1. Whereas the dx plus e, it's only multiplied by the x because the x squared plus 1 squared canceled out. Now, this allows me to say, well, okay, in this one, and this is the first time I've done this. Before, you really didn't need to. I think in this one it's helpful to square out this x squared plus 1 squared. I just said, well, that's equal to x squared plus, x to the 4th, x squared times x squared, plus 2x to the 2nd, plus 1. That next one, the bx plus c, I went ahead and separated that and shown what is b going to be multiplying and what is c going to be multiplying. Notice if you distributed the x through here, you'd get x cubed plus x, but then you know that you're going to have to multiply bx times that, so that gives me bx times x cubed is bx to the fourth. And then I would have a bx times x times 1, that's going to be the b as a coefficient of x squared. The c is just multiplied by the x cubed plus x there, so no big deal there. The d is going to be multiplied by an x squared term, and the e is only multiplied by x. So now, once I help set that up, that really does help solve out the problem. Let me show you why. For the a, I know I should be able to solve for it by just setting x equal to 0. I do that. If I set x equal to 0, then every one of these that still has x as a factor becomes 0. So the b, the c, the d, and the e all get multiplied by a factor of 0. Well, if I plug a 0 in with a, I just get the constant 1. On the left-hand side, I still had my constant of 2. So I know 1a is equal to 2. Well, a is equal to 2. No other number plugging in for the variable x helps in this problem, so instead I start looking at powers. The x to the fourth power. Well, the coefficient of x to the fourth on the left-hand side is 0. That's where that 0 comes from. Then I look at what coefficients of x to the fourth could you possibly have on the right-hand side. And you can see that it's just going to be ax to the fourth plus bx to the fourth. No other letter can be a coefficient of x to the fourth. So that tells me yet again that I know b is just equal to the negative of a, so b is negative 2. I look at the x cubed term, and I can tell a is not a coefficient of x cubed, b is not a coefficient of x cubed, neither is d or e. The only coefficient of x cubed is c. Well, there is no x cubed term on the other side, so I know the coefficient of x cubed is supposed to be 0. That means I know c is also supposed to be 0 since it's the only coefficient of x cubed on the right-hand side, and its coefficient of x cubed is supposed to be equal to 0. So I know now a, b, and c. In order to find out d, I just think of the x squared term. Yet again, you don't have an x squared term on the left-hand side, so you know the coefficient of x squared is supposed to be 0. Look on your right-hand side of your equation. The coefficients of x squared, you'd have a 2a. That's where that came from. You would have a bx squared. C is not a coefficient of x squared, but d is. So you're going to have 2a plus b plus d. All of those are my coefficients of x squared. We already knew a was 2, so I said 2 times 2 is 4. And then I have plus b. Well, b was a negative 2, so it's plus a negative 2 plus d. I know 2 plus d is 0. That gives me d is equal to negative 2. Now, finally, I go in and I solve for e, and I said, well, e is a coefficient of x. What are my other coefficients of x on the right-hand side? The only other coefficient of x would be c. So I know c plus e has to equal the coefficient of x on the left-hand side, which is again 0. So I know 0 is equal to c plus e. I already knew that c was equal to 0, so now I know e is also equal to 0. So now I take all of this information and I use that to create up my integral. The original integral for this problem is going to equal a over x, 2 over x, plus the integral of bx plus c. Well, that's going to become negative 2x plus 0 over x squared plus 1, plus dx plus e over that x squared plus 1 quantity squared. But again, that dx plus e, that's just going to be negative 2x plus 0, so I get a negative 2x again over that x squared plus 1 quantity squared. Now, I have the integral set up. The first and the second one are pretty straightforward. The third one, we'll talk about that. The first one, anytime the degree of the numerator and denominator differ by 1, it is a natural log. This is going to be 2 natural log of the absolute value of x. The next one, in order for this one to be a natural log, you would need to see a positive 2x in the numerator. Well, that's no big deal. You just need to factor that negative out. That's where that minus sign comes from, and then you say minus the natural log of the absolute value of x squared plus 1. The next one, what I did here is I've used substitution, and I can say, well, I know that this isn't a natural log because the degree of the numerator and denominator don't differ by 1, but how can I handle this? Well, I said let's let u equal x squared plus 1, so du is 2x dx. I had a negative 2x dx. I went ahead and factored that negative out to the outside. And then I can say, well, that 2x dx that would be left on the inside, all of that becomes du. And I just have 1 over u squared du. I thought of that as u to the negative 2. Whenever you integrate u to the negative 2, you'd say, well, it's the power rule. You add 1 to the exponent, becomes u to the negative 1. Divide by that new exponent, negative 1. Plus the constant integration. We know that that's better written as negative 1 over u to the first plus c. So now I'm going to bring that down here, and I can say my first two I already had done. My next one, it would be minus a negative 1 over u. Well, that's plus 1 over u. That's why I turned that back to a plus. 1 over u, instead of putting a u, put what u is equal to. You know to do that. So I had the x squared plus 1 in the denominator, plus our constant of integration. To make the final answer, I just combine the two logarithmic functions, and I can say this would be the natural log of x squared, and then divided by the group x squared plus 1, and then we have plus our 1 over x squared plus 1 plus our constant of integration. Now, this problem I've worked with, the case 4, is a nice case 4 problem. Case 4 problems can get brutally difficult. But now, of course, brutally difficult can also mean absolutely gorgeous depending upon your mindset. But I just didn't want you to think that all case 4 problems look exactly like this. If you'd like me to do a video of a more challenging, frustrating, fun / gorgeous case 4 problem, I'll be glad to. I just didn't want to frustrate you here as you're trying to learn the information. Let's look at the last case. And the only reason this is the last case is just because I chose to put it last. It's really not the hardest case. Case 3 and case 4 are by far the hardest cases. Case 5, I just threw this in here. Oftentimes, and in fact, several of the early homework problems you'll have to do this in. Case 5 is just when you should use long division first. And then after you use the long division, you could have a problem resulting with case 1, 2, 3, or 4. Typically, the problems that use long division first are not that difficult of problems. So case 5, how are you supposed to recognize case 5? Anytime you look at an integral, if the degree of the numerator is greater than or less than the denominator, you should use long division first. So that's what I wrote here. You should use long division first anytime the degree of the numerator is greater than or equal to the degree of the denominator. So I'm looking at this problem, x to the 4th plus 1 over x cubed plus 9x. The very first thing I do is long division. X cubed plus 9x divides into x to the 4th plus 1. X cubed goes into x to the 4th, x times. X times x cubed is x to the 4th. X times 9x is 9x squared. I know I had to subtract that out, and as long as you're canceling out the first term, you're doing what you're supposed to. So notice the x to the 4ths cancel. Then you would have minus 9x squared. Then you'd bring down your plus 1. So what I'm trying to show here is that this original integral is equal to the part that divided evenly is its own separate integral now. So it's going to be the integral of x with respect to x, and then plus we'll have the integral of whatever we had remaining, that remainder of negative 9x squared plus 1, it's still divided by our original fraction. But you'll notice what I did here, I just went ahead, since I knew I would need that factored anyway, I went ahead and factored an x out of that denominator and said that's just going to be x times the irreducible quadratic factor of x squared plus 9. So now, after you've done the long division in the first step, you can see that you still have a problem that's a resulting, this would be what I called case 3 earlier. I have an irreducible quadratic factor to the first power. So I need to break apart that fraction, the negative 9x squared plus 1 over x times x squared plus 9, and I'll say, okay, that's going to equal some number a over your first factor of x plus a linear factor of bx plus c over the irreducible quadratic factor of x squared plus 9. Now, what I've done with that is I said, okay, let's multiply this entire equation by the least common denominator of x times x squared plus 9. So notice my left-hand side stays negative 9x squared plus 1. The right, you're going to have a times x squared plus 9, and you have the group bx plus c times x. Now that I've done that, I can say, well, you should be able to solve for a by letting x equal 0. I let x equal 0. The left-hand side of my equation is a 1. The right-hand side, the b and the c get multiplied by 0, but a gets multiplied by a 9. I get 9a is 1, thus a is equal to 1/9. Now, no other number can be plugged in for x to help you solve for b and c, so instead I start looking at the variables in the problem. I look at the second power of x here. I know the coefficient of x squared on the left-hand side is a negative 9. That's where that negative 9 comes from. The coefficient of x squared should be negative 9 in this problem. How could I possibly get coefficients of x squared on the right-hand side? And I can see a is a coefficient of x squared, b is a coefficient of x squared. Please make sure you see c cannot be a coefficient of x squared. It's only a coefficient of x to the first. So I get ax squared plus bx squared. So my coefficients of x squared should be negative 9 is equal to a plus b. Well, I already know negative 9 is the same thing as negative 81 over 9. I just got a common denominator with the 1/9 that I knew a would equal. So negative 81 over 9 is equal to 1 over 9 plus b. Subtract 1 over 9 on each side. That gives me b is equal to negative 82/9. Now, in order to get the last variable c in this problem, I saw that c is a coefficient of x in this problem. A cannot be a coefficient of x. B cannot equal a coefficient of x. B is only multiplying x squared since it's bx times x. So the only coefficient of x on the right-hand side is c. Look at what the coefficient of x on the left-hand side. There is no x, which means its coefficient is 0. Thus, c is equal to 0. I can come down here, the original integral, I've went ahead and solved the first part. The integral of x dx is 1/2 x squared, of course, plus I have a over x, well, that's my 1/9 over x, plus bx plus c over x squared plus 9. So I get negative 82 over 9x plus, again, c is 0, so I don't have to worry about that. Now, when I'm looking at this integral, I know that it differs in degree by 1, so it has to be a natural log of the denominator. But the only way that that would happen is if that numerator had a 2x. So notice all I've done is I just said to myself, well, this is a factor of negative 41 over 9 times 2. I'll factor that negative 41 over 9 out in front of it, and then it leaves me a 2x dx, which is precisely what I needed. Anytime the derivative of the denominator is in the numerator, it's going to be the natural log of the absolute value of that denominator. And you'll notice in this step I did go ahead and say the second one is just 1/9 natural log of x. This third one becomes minus 41 over 9 natural log of x squared plus 9 right here. And then we have two logarithmic expressions in the problem. I went ahead and condensed them to 1. This is going to be the natural log of the x to the 1/9 power. I said the 9th root of x. And then we know we're dividing by this one since it's a subtraction of a logarithm. And then you could say it's x squared plus 9 to the 41/9 power, or I went ahead and put it in radical form as the 9th root of x squared plus 9 to the 41st. And then all of that is plus our constant integration, and don't forget the first easy part, the 1/2 x squared. Now, this concludes the 5 different types of partial fraction problems that you're going to see in this section. Not all of these are as easy and as direct as some of these examples that I've worked, but I think that this gives you the game plan for all of the problems. Please make sure you look through my homework solutions and that they make sense to you. Some of the homework problems did get more fun than these, but this gives you a very good game plan, point of attack, and strategies for how to work out these problems. Good luck with these, and please let me know if you need any help. I absolutely love working these problems, so I don't mind helping you out at all on this.